Okay, so this is section 11.6 and it's called volumes of pyramids. Here's a sample of a pyramid made out of paper. It's got hexagon on the bottom, it's hexagonal base, and it's got triangular, and they all have to be the same kind. I mean, they're all the same ones, because this is a regular hexagon. Then the sides coming up off of it that meet in a point, which makes it a pyramid. They're all triangles, yeah? So that's an example of a pyramid with a hexagon base. Here's another sample of a pyramid with a square base. Y'all see it? I don't know if you can see that very well on the tape right there, but it's got a square base. And because it comes to a point on flat sides that come up, it's not a cone, it's a pyramid. It comes up on flat sides to a point. We call it a pyramid. This is a square pyramid. This thing is called a hexagonal pyramid because of its base. Okay? So we're going to try to find the volumes of these things today. This right here is just a regular prism, right? Just a square prism. Y'all see that? I hope you can see that on there. Just a square prism. And it happens that this pyramid that I have right here fits right on top of it. In other words, the square that makes up the base of this pyramid is exactly the same as the base of this prism. Okay? So my question is, oh, by the way, it's just as tall. And it's kind of hard to tell that it's just as tall. It's kind of hard to see, but it is. It looks like it's slightly a little bit more tall. But the reason why is because it takes plastic to complete this right here. And it looks like it's a little taller than this, but the actual volume, the actual empty space inside is as tall as this is. So this has the same height as this. It has the same base as this. My question is, if those are all the same, how many times would I have to fill this up if I poured it in there? Any idea? What do you think? One? Okay.
According to the book, it says.
Yeah, I don't want you to be according to the book, so don't talk to me about that yet. Don't anybody look in the book. Let's see how many. How many do you guess?
One and like a quarter.
What?
1 1/4.
1 1/4. Okay. So I'm going to fill this up. Takes a minute to do this. Salt. Salt's cheap. Behaves like sand. It's kind of hard to fill the corners. So I'm going to try to shake it down a little bit. There's a little bit of a peak on that, but there's also some missing areas in the corner. So I'm going to guess that's about right. Okay. So pour that in there.
Oh, no.
How many do you think?
I'll have 3.
2
2.5.
2.5 or 3? Okay. Whoa, got a little carried away there. Whew, that was spilling. Okay, that's about right. So I'm gonna pour that one in. How many do you think?
1 more.
You think it'll hold one more?
Yeah.
This is really tricky to do this last part. Pouring it out of there into this can be kind of tricky, but let's see. Let's see if it'll hold all of this. That's a little bit. I'm going to do this on purpose. It's a little bit, I got a little bit much. I'm just going to dump it off right there. Okay, about right there. Okay, so I'm going to pour some of it in here, but it's going to be tricky to try to get it in all the corners and everything. You think it'll hold it?
Yes.
Mm-hmm.
I think I overfilled a couple of them. Anyway, it does. It's supposed to hold all of it. Okay? So the moral of this story is, if you can find the volume of this, just divide it by 3 and you'll have the volume of this. Right?
Mm-hmm.
And so from all of that demonstration, what we have here is that if you've got a cube, well, it doesn't even have to be a cube. It just has to be a rectangular prism of some kind. I'm going to make it a cube because that's the one we just talked about, but it doesn't have to be a cube. If I have a cube here, and this is A, well, maybe I won't make it quite a cube. This has a length of A and a width of B and a height of C. We know that the volume of this is A times B times C. Right?
Yeah.
Well, if we have a square pyramid or a pyramid that has the same A and B here, And if I bring that to a point up at the top like this, like that, and this has the same height as C, then the volume of this is going to be 1/3 of A times B times C. Right? That's what we just saw and demonstrated right there. So it's the only difference between doing what you did yesterday as far as volume goes and what we're going to do today is we're going to have these things come to a point instead of just come right straight up the sides. We're going to bring them into a point. And what happens to that when you do it is you only get 1/3 the volume. And to summarize this so that it's not specific to a cube, but to any pyramid, this is what it is, to any particular pyramid that you get, it's going to be the base area, even if it's longer like this, if it's a rectangle like this, you've got some sort of pyramid like that. If this is the base area, which I'm going to call capital B, that would be little a times little b. That would be the base area. The volume of a pyramid is going to be 1/3 of the base area, whatever it is, whether it's a rectangle or a square or whatever, or even a triangle. Whatever the area of the base of it is, times the height, that would be the height from here to here, like that, from the center of this middle up to there, like that, perpendicular to it. That would be H. I didn't do that very well. This is H. Anyway, it's kind of hard to see. I'm not going to draw it over there like that. This is H right here. It's 1/3 of the base area times the distance from the base to the point. Okay, that's it. That's all there is today. We're going to do several examples, show you how to deal with it in different circumstances. But that's really all there is today, is that the volume of a pyramid is 1/3 of the base area times the height. And the base could be a triangle, could be a hexagon, like I showed you with the green thing, could be a square, could be a rectangle, could be just about anything. But whatever comes to a point above that base, the base area times the height will be the volume. Divided by 3, sorry. Divided by 3. So that's really the only concept we've got. So let's go and see if we can just draw. Take a look at example 1. It's on the bottom of page 636. It says, find the volume of the pyramid. Okay, we know it's going to be 1/3 the base area times the height. Now look at the pyramid that they've got drawn for you there. The base of it is what? What could you call the base of it? What should you name it? Go ahead, say it out loud. The base of that pyramid could be named what? A right triangle. That's what I'm after. That's a right triangle. See the little red box in the middle of it? And the area of a right triangle, folks, the area of any right triangle, if it's a right one, you can use this as the base and this as the height because they're perpendicular to each other. Maybe you discovered that in the last section, I hope. And so in this case, the base area is going to be 4 times 6 cut in half because it's a triangle, 1/2 base times height.
Yeah.
Okay, and so that's going to be 12. The height is the red line that you can barely see out to the side there. It's the red line extended from the peak of it, or the point of it, perpendicular to the base, and that's 9. So she's going to be 12 times 9. Divided by 3. Because it comes to a point. So I'm saying this is the base area, and if I change these to what it actually is, it was 4 and 6. And so the area of the base is equal to 12, because 6 times 4 is 24, cut in half is 12. Are you with me or not?
Yeah.
Pay attention, people. So I got my 1/3, that's part of the equation, times the base area, which is 12, times the height, which is perpendicular to the base, which is 9. And if you multiply those 3 things together, you get the volume, which is 36. You okay with that?
Yeah.
Cool. Move on. Look at example 2. Is it says originally Caffrey's pyramid had a height of about 144 meters. That's 14.5 stories. We don't have anything remotely close to that in Rexburg. Well, sure. Anyway, 144. No, it's way more than that. I lied. It's way more than that because that's what it would be if it were 144 feet. It's more like it's almost 50 stories tall. And a volume of about, holy crap, look at that volume, 2,218,800 cubic meters. We're supposed to find the side length of the square base. So now now they're gonna mess this whole thing up for us. We're not looking for volume. We know the volume. We got to look for one of the dimensions. So here's my square base pyramid. Comes down like that. And they're telling us that this height right here, H, that's from the peak down to the middle of the floor here, the height is 144 meters. But I don't know what these little lengths are here. I'm going to call them little b for base. And they told us it was a square pyramid. So the area of the base right here, this guy right here, that's capital B, is going to be little b squared. Would you buy that?
Yeah.
Okay. So we're going to use our formula. Volume equals base, 1/3. The base area times the height. I'm going to fill in what I can. That dude right there is huge. What was it? 2,200,000 what?
218,000.
18,000. Sorry? 800, like that?
Yep.
Okay, equals 1/3. We don't know what the base area is, but we know it's going to be b times b because it's a square, times the height, which is 144. You understand all the fill-in of the details that I could possibly fill in? You following?
Yeah.
Okay. Can you take a third of 144 and get anything reasonable? 144 divided by 3 is what? Yeah, or can you even do it?
48.
48. So if I take this number times this one, then the right side turns into 48b squared. You with me there?
Yeah.
Now I got to divide that by 48. Take this monstrous thing, divide it by 48. That's the next move, and tell me what you get. $46,225. And there's no decimals? There are decimals?
No,
It's just clean, nice straight. And now I've got to square root that in order to solve for b because that's the inverse of squaring. So what is b?
215.
Exactly?
Yep.
And that's in meters. That's a little over the full length of 2 football fields. That's a big pyramid. That is a huge pyramid. Okay. So anyway, this is how we did it. We used the formula. We filled in what they gave us. They gave us volume. They gave us height, but they did not give us the base area. But they did tell us the base was a square. So we know the base area is going to be side times side, which is side squared. And then we went about, after you get this written down and you fill in what you can, now it's all algebra. We took this times this to get 48. We divided 48 into this to get this number, and we square rooted this number to get the b, which was the length of a side. Did you follow all that? Cool. Very good. Moving on. Look at example 3. Example 3 says, find the height of the triangular pyramid. This is the information they give us. They tell us, it looks like they're giving us height, but they aren't. They're giving us volume. It says the volume is 14 cubic feet. And the base is a triangle whose base is 4 and whose height is 3. So we gotta break this up a little bit in order to use our formula. So we have a triangular base this time. So hang in there. Triangular base this is going to be hard to draw, but the triangular base is like this, where this is 4 and this is 3, and then it's going to come down like that. That's going to be our pyramid. I hope you can kind of tell what that is. This is 4 and this is 3, and they are perpendicular. And so our formula, which we go to, is volume equals 1/3 the area of the base times the height. This time, the area of the base is 1/2 4 times 3. Because the base is a triangle whose area is 1/2 base times height. Are you following me? Times the height, which we don't know, but we know the volume is 14. So you substitute in whatever you can. And this thing is the part that's going to change because the base can change to any shape they want. This particular base is a triangle whose base is 4 and whose height is 3. That's what I have here. You with me? And the area of a triangle is 1/2 base times height. So now I got to deal with all those fractions. 1/2 times 1/2 is 1/4. 4 times 3 is 12. So I did a little bit of cleaning that up. 1/4 of 12 happens to be 3. You okay with that? I'm just multiplying again. And I got a 14 over here. So we get an ugly height that's 14/3 when you divide. But you just keep cleaning up the arithmetic until you can solve for h by division right there. that what they got, or did I screw this up? Okay, something happened. 1/2 3 times 4. Volume's 14. 6 times 8, 1/3 of 6 is only 2, so what did I do wrong?
You put 1/2 in the same spot.
Oh yeah, 1/2 instead of 1/3. Boy, thank you for that. That should have been 1/3. Sorry about that. So this should have been 1/6. We okay? You understand the error and the mistake? Yeah, okay. That should be 1/6. 1/6 of 12 is 2. 2 does go into 14. Copy error. Sorry. I make them all the time. And the units on this was measured in cubic feet, so this is going to be 7 feet for the height. Okay?
Mhm.
Sorry about that error. I'm used to writing 1/2, so I'll write 1/2. Okay. Take a look at example 4. This is going back to the idea that, you have to remember this, it's always true for all volumes, whatever the scale factor is, which is a linear factor, whatever the scale factor is, whatever it is, if you cube it, you will get the volume factor. And you have to use the volume factor as part of your proportion for volume calculations. So take a look at what we've got here in example 4. It says pyramid A and pyramid B are similar. Thank goodness, because none of this applies unless it is. It says find the volume of pyramid B. That's the little one. What we do know, if you look very carefully, is that their heights compare in a ratio of 8:6. See it?
Mhm.
8:6. That reduces to 4:3. So my scale factor, linear scale factor, is 4 compared to 3. I have to cube that. And if you don't know this, then you probably have to ask your calculator what it is, but 4 cubed is 64. 3 cubed is 27. That's my volume factor. Y'all see how I arrived at it?
Mhm.
So now my proportion is going to be 64 is to 27. That's big to little. Is the same as big volume 96 is to little one. I'll just call it V for the volume of the little one. Do you understand how I set this up?
Mhm.
You gotta cube your scale factor to get this piece of the proportion because we're doing volumes. This was big to little, so this has to be big to little. So we took the big volume, which they gave us was 96, that goes on the top. So I get, in the cross multiplying, I get 64V equals 27 times 96. Don't know what that is, but I have to divide. Volume is going to end up being 27 times 96 divided by 64. Whatever that is, that's the volume of the little one. It came out perfect. 45, you said?
40.5.
Oh, 40.5. And that will be in cubic units, and in this case, cubic meters. So very much like yesterday, it's just that we're dealing with volumes of pyramids. The volume factor has to be the scale factor cubed. And then you got a proportion you can cross multiply and solve. Didn't have anything to do with our formula. Has to do with the way scale factors and volume factors are related. Okay, one more example. This thing we're going to do now is a composite, they call it. It's made up of different geometric shapes. So take a look at example 5. It says, find the volume of the composite solid. And what we've got there is just what I showed you was this. This is what we've got, what it looks like, right? So what we've got is a prism. The volume of a prism, I'm going to make that a little bit better than that. It's a volume of a square prism. Square prism added to the volume of a pyramid, right? Now the volume of a square prism is, that's what I do next. This is my general strategy. I've got a square prism added to the volume of a pyramid, and a volume of a square prism is length times width times height added to the volume of a pyramid we learned today is 1/3 the base area times the height. So I start to put some things in. I go to my picture, and it looks like length, width, and height are all 6. So right here I have 6 times 6 times 6 plus 1/3. Now, what's the base area of that pyramid? That pyramid has a square base, and what are its dimensions? What's this? 6, what's this?
6.
Can you see we can get that from the bottom of the square?
Yeah.
Okay, so I've got the base area, which is a square, so I got 1/3, 6 times 6. That's gonna be the base area times the height. How tall is it?
6.
6? Good grief, ton of sixes. So this one's gonna be 216 if I recall my cubes, is that right? 6 cubed, 216? Plus, I'm gonna do 1/3 of one of these sixes. That'll give me 1/3 of 6 is 2, and 2 times 36 is 72. So 1/3 of 6 is 2, and 2 times 6 is 12, and 12 times 6 is 72. Do it that way too. 216 plus 72 would be 288?
Yeah.
And what's it measured in?
Meters.
Meters? So just like we've done all composite things, when we want to cut something out or add a couple of things together, it's the volume of one geometric shape plus the volume of another geometric shape. We write down the formulas that we know for both, and then we start to fill in the gaps. Once you've got all the numbers filled in, if you can just do it without having to figure something, once you got all the numbers filled in, do the arithmetic. Not too bad, is it?
No.
You able to handle this?
Yes.
The assignment is not that long. As a matter of fact, it's actually quite short. We should be easily done before the end of the period. The assignment is numbers 3, 4, and 11 to 17.